Welcome. This video is going to get into 15.1, where we talk about what is a logarithmic function and how do we evaluate it. So the inverse of an exponential function is called a logarithmic function. Right? We've talked about how to find inverses on simple things like if we had y equals x squared, right, we switch x and y and all that. But this is a little more complicated. If we look at a graph, so remember we talked about an inverse graphically is a reflection over this line, y equals x. So if I put a typical exponential function on here, looks like this. All right, so if I graphically try to find the inverse, it looks like this. All right, so if we called this y equals 10 to the x, this would be the inverse of that function, which is log base 10 of x. All right, so exponential functions, 10 to the x, its inverse would be a log function. I'm going to call this log base 10 of x. This is actually the common logarithm, and you don't have to write the 10. So log of x automatically means it's base 10 because it's the most common one. Similar to when we had square roots, we didn't have to write that little 2 here because it was the most common one. But when we're doing cube roots or fourth roots, we have to write that number. All right, so let's say I had an exponential function y equals 6 to the x. Well, its inverse is a log function, log base 6 of x. We're going to get into on the next slide, we'll get into how these things, how we can go back and forth between them. But let's talk about exponential functions in general. If we look at the apparent graph, that looks like this. Our domain for exponentials, we said, is always all real numbers, right? And our range for this parent happens to be 0 to infinity. Well, if I look at the inverse, do you remember what happens with domain and range? They flip-flop, don't they? So the range of a log function is always all real numbers. This is what we learned in on our current test. This is what we're learning now. If you know one thing for sure, for a log function, the range is always all real numbers. In this case, if I compare the two graphs I have up here, the domain, right, notice that this graph right here, folks, without me running over, the domain is 0 to infinity, isn't it? Okay, so this is just an introduction. We're going to get more familiar as we use different parts of this section. So there's a few ways to look at it. We want to be able to translate something from that might be an exponential form, translate it into base form, or from base form to exponential. So there's two ways to look at it. This one comes out of the book. This is what we talked about an exponential equation is. We had a base, right? Our base was always positive and it wasn't equal to 1. Right? If it were, remember what we learned in this last exponential section, right? If it was between 0 and 1, that was decay. And if it was greater than 1, that was growth. So here's our exponential equation. Well, B is for base. Over here, if I'm translating it into its log equivalent, the base is the base of the log. Okay? So b to the x equals a. So when I rewrite it with a log, we like to call it, used to call it the polar vortex. We would say log base b of a equals x. Log base b of a equals x. And we can go backwards too. Here's a way that Mr. McCaskey likes to look at it. He says, well, here's my exponential form. There's a base, it's raised to an exponent, and it gives us an answer. If we want to translate it into its equivalent logarithmic alternate form, well, log base whatever the base of the answer equals the exponent. So you notice that the answer and the exponent switch sides. I know this is clear as mud, right? Let's do this example. So we're going to look at this one. 4 to the third equals 64. Well, let's identify the pieces. Well, the base is 4 here, isn't it? The exponent is 3. So if I'm going to write it as a log, that base has to be the base of the log. And then these two pieces basically switch sides, don't they? The log base of the answer, in this case the answer is 64, the log base of the answer equals the exponent. Right? So that's this equation here. Now, let's look at number 2. We'll call this 1, 2, 3, and 4. So notice that the log, the base of the log is 5. So that will be our base of our exponential. The exponent is sitting here, right? We're going to be switching these other two pieces. So 5 to the negative 2 equals 1 over 25. And we can put that in our calculator and confirm that, right? Okay, let's look at number 3. We'll do this. We'll identify. So our base here is 2 over 3. Our exponent is p. Our answer is q. So this is going to be the log base 2/3 of q equals p. Let's try 4. Again, here's our base, isn't it? The base, 1/2, and we're going to raise it to the exponent of n equals the answer m. All right, let's try another one. Okay, if I come back here, I'm going to rewrite this over the top, if that helps. We're going to say the log base. I always like to start with the exponent because that's the one we're used to. The base raised to the exponent gives us an answer. And when we're going back and forth between the alternate forms, we know where the base goes. These two pieces switch sides, don't they? So the log base of the answer equals the exponent. Okay. Base of 3. So log base 3. Notice this is a subscript, isn't it? Log base 3 of the answer, 243, equals the exponent 5. To me, it's a little easier to go from exponent to log, but we want to be able to go both ways. So here, log with a base of 3 over 4 of the answer, so of s, equals the exponent r. Now let's take these two and go backwards. Base of 4. 4 raised to the negative 3 equals 1 over 64. Okay. 1/5 raised to the w equals v. So we have this, like in the one class we used to teach, we called it the polar vortex because that was going on in the weather. So this is us taking an exponential or a logarithmic and writing it in its alternate form. Okay? Now, this is helpful. We have a history of working with exponents. We are comfortable with it. Logs are all new and harder for us to have a kind of an intuitive feel for them. So what we're saying here is we can take something that's written as a log and rewrite it as an exponent to try to get to the answer. Okay? I'm going to end here and start the next video on this section.